case, but within a scenario, it is. Watch this. For a specific IB, as I increase VCE, then my IC is not increasing by that much. It's staying pretty stable. Does that make sense? Even though my VCE is trying to pump more current in that primary circuit or secondary circuit with the output. Does that make sense? Okay, same thing. So every time, so another region where I have a larger IB, so we know this IB2 is going to be larger than IB1. Hence, you're going to be at a different level for IC. But you get to see that IC stays the same as long as IB is within that region. Does that make sense? Okay? And then you could say, okay, what's the relationship between IB and IC? So let's say you pick a point here. You go over here, you pick out the IC of IB2, or you can call it IC2, and then you do the IC2 divided by IB2. And that gives you beta for that scenario. Does that make sense? That's it. That's one way. So we're going to do several things here together. So I'm going to build a circuit like this one. Let's try to think, what is it I'm trying to do here? Remember, I like to start with the extremes. What would be my max saturation current in the secondary part? Well, that happens only, and this is why I sent you to go to your corners to figure out the relationships between currents, VCE, and all that, right? When do you have saturation? When VCE is 0. In other words, you have max current in this loop. In other words, it's VCC divided by RC. So the max current for this circuit that you will ever extract on IC will be 15 milliamp. Do you agree? That's it. What if I reduce this resistor? The current is going to increase even more. Do you agree? So there is a limit this transistor can handle. It's 200 milliamp. So I have room to pick a resistor here as long as I don't pass what? 200 milliamp on that transistor. That's on the spec sheet. Do you agree? So any value for RC here is simply to reach the max saturation. Does that make sense? Now what's going to happen is as I change IB, if I reduce IB from that point, then IC will reduce, but it will never reach, or if I try to increase it, it will never reach beyond this saturation point. From this point on, I can play with IB because it will play with IC through beta. And I can bring it down. Does that make sense? And what else? Well, how can I play with IB? Well, I have two ways. I can play with a power supply here. Why? Because the current IB will be this minus VB, which is 0.7, divided by RB. So if this changes, then the current IB changes. What if I keep this at a certain voltage but change this? Same deal. You have two choices to change IB here. Does that make sense? So I can change VBB or I can change RB or both, especially in scenarios where I need to keep IB steady. You with me so far? So to do this, we're going to simulate this as a current generator because I want IB to be what? Steady. Now, you don't have a current generator anywhere in your lab. Does that make sense? So how do you simulate that? That means every time you're going to have to reset, either adjust your RB or VBB to keep the same IB for all the scenarios. Now, this one you can do what? Modify. VCE, change it. Does that make sense? As you change it, how VCE here is going to depend on VCC. You with me so far? So you're going to change your VCCs and see how far you can go. And guess what? The max you can get, and this is where the operating point comes in. The max point you can get is VCC here. This is the load line. We have another lab for that. This is going to be a straight line, by the way. And this here will be an IC of SAT. Based on this scenario, that's 15 million. If I wanted 150 million, I would drop this to 100 ohm. Does that make sense? If I wanted to get to the max current that transistor can handle, I can go to 15 ohm. Below that, and I'm asking for trouble. So is everybody seeing now how you converse? This is why you need to justify. Now, I gave you these circuits, but in the future, you're engineers, you're not technicians. Technicians are given a circuit and troubleshoot. Does that make sense? You're designers. You have to think of these relationships before you pick what value resistor do I really need here. You're building the damn circuit. You with me so far? You're it. You're the matter expert. You know, you're designing something new, a controller arm, or whatever it is that you want to do, or an amplifier. You have to think of the specs. What is it you need? Well, on my secondary circuit, you got to think of the power consumption there. If it's a speaker or anything. If it's a motor, how much current do I need to drive that motor? Does that make sense? Based on that, then I'll pick the right transistor, etc., etc. I could set it to saturation and it will drive the motor. I can take the motor and saturate and cut off. You with me so far? And if I want to slow it down, I start doing what? Moving my operating point down. So I can, here how am I going to do this? Yeah, I can have what do you call it, potentiometer here. Does that make sense? And let's say this is a motor right here, this one. Well, you know, I could reduce its RPM. All the way down to where it stops and all the way up where it will max out. It's a current control device. You with me so far? That's what a transistor is for. The beauty about it is my primary circuit, I don't need that much current because there's a relationship between them, beta time. So my control area does not consume a lot of energy. You with me so far? Most of my energy is right where the load is. That's the whole point. Does that make sense, folks? Okay? So you can think of a transistor circuit like this. This is the control, this is the objective. This is where you want the action to be. This could be a speaker, this could be a motor, that's your load. Does that make sense? Depending on how it operates, that's what you need to figure out what I need to do at the input. Getting it? Okay, good. All right, so I'm going to build this circuit, and we're going to play with it. And I have a procedure, and I'm going to go through these procedures. And then I built this circuit here. Well, guess what? What did I just do with this one in particular? I brought in 15 volts to this point, right? Y'all agree that this point is 15? So what do you think it's here? 15. This is, instead of having dual power supply, I can do it with what? A single power supply. Just need to figure out the right resistor to throttle down IB. Yep?
Would that also make it a tail?
No, this is equivalent to doing what? Doing this without this wire. Does that make sense? But here, you have two independent power supplies. Here, you have only one. You don't have two 9-volt batteries for, let's say, my tester. Do you agree? For the wires. You only have one source if you have a toy. Do you agree? Right, so what are you going to do when you have only one single battery or a bank of batteries, but you don't have two separate power supplies? Well, you're going to have to make sure you bring the potential to where you need it to be. Does that make sense? Okay? And this is typical configuration of transistors using a single power supply. Then, what was the point of this doing this? Well, the point of this one, procedure 2, which is really to look at IB versus IC. That's what I was interested in. So procedure 1, I'm interested in IB versus VBE. So this here should give me what? A graph that looks like a diode. Does that make sense? And then this one here, yep.
So
let's go back here.
Now for part 2.
Part 2.
So
part 2, I'm interested in IB-IC.
Yeah, but my question was, if there were like two power supplies, RB would be lower.
No, not necessarily. Not necessarily.
Is that-
So let's look at what it says here. Notice what I'm doing with RB. I'm increasing RB. Does that make sense? This 100K that I started with was the minimum that you needed to be at saturation. By increasing RB, I'm decreasing IB, which means I'm decreasing IC, and I'm getting into these regions. Does that make sense? So like I told you before, I'm an engineer. I start from an extreme and drop because I know how to get here. You with me so far? Then it's real easy to go below. So I'm not guessing. I know where my zone is. Troubleshooting is the same way. You need to know where this is spec'd at. Great. What's my range? Now I know where it's at. Does that make sense? Okay? Good. So here you can tell that I'm doing what with the RB to answer your question?
Increasing it.
Increasing it because I want to decrease IB. So I'm going backwards. Does that make sense? I'm going to go from max IB2 all the way down to min IB until the transistor is completely cut off. Does that make sense?
Increasing RB to.
By increasing RB, IB is going to decrease. And remember, your transistor is a current controlled device. In other words, IC will decrease proportionally. We have to prove that. That's why I'm looking at IC versus what? IB. Can we, if it's a straight line, well, we don't know that until you see. If it's a straight line, then beta is the same across. Do you agree? Right, because that would be the slope of the line. The ratio of IB over IC over IB is the slope of the line. Yep.
You said increase RB to decrease IB
Yes.
and IC as well.
IC will decrease automatically as you decrease IB. Notice here, I am not touching VCC. I'm leaving it at 15 volt.
Yeah.
Does that make sense? And I'm not touching RC. I'm leaving it at 1K. In other words, I know my max current to start with is 15 milliamp. And I'm going for 15 milliamp down. Does that make sense? For IC. Yep.
So is this what you mean by throttling the resistor?
The throttling the input, yes. Like playing with this. I could have a potentiometer to do this, or I could just take out a resistor, put another one for the next scenario, and you collect data accordingly. Does that make sense? Okay. So, and that's what a lab is. It's an experiment. You have to go through all these scenarios. So, procedure 3 is what you're going to see out there, with minus the load line. That's another lab. So notice here what I did is I'm trying to throttle IB to be the same across the scenario. So what is it I'm going to be changing? Notice here my simulator, I'm going to teach you this. The simulation here is different than the .op. Does that make sense? Here what I'm doing is I am actually creating what we call steps or a sweep. In other words, I am sweeping. Every time I change this, I keep this one for until it's maxed. I keep this for a certain value, then I come back, change this, and then for another value of IB. Then change this again, sweep for another value of IB. Then change this again for another value of IB. So we get to see two sweeping things going on at the same time. Does that make sense? To create a multi-scenario in one graph. So let me just take out the load line so you're not confused. This is the next lab. Load line is extremely important because you will see it crosses these scenarios. And you can pick any scenario against the load line. You can say, oh, I want to be here at this IB and IC. Perfect. Does that make sense? And that's how you tune your circuit. That's how you figure out, okay, I've got all that scenario laid out. Where do I want to be? Do I want to be closer to saturation, closer to cutoff, or somewhere in the middle if it's a small signal amplifier, for example? Okay? So, without further ado, let me go ahead and do this one. So I'll do it again from scratch here. So I'm just going to go over here.
Can we turn off the lights?
Yeah, yeah. and I'll give you this file. And I need you to go back over the LT Spice you submitted yesterday. Go over it again. Does that make sense? I'm giving you that opportunity. I'm not putting zeros or taking points off. I need you to go back and fix stuff. Be expressive as to what is it exactly you're doing. You got it? Okay? I can't write a whole bunch of things here on the board. I have to get to the meat. I have to get to what we're going to be doing. Does that make sense? You have to explain that. The burden is on you to do that. So let me go back here. File, new, schematic. Let's save it where I needed to save it. And that would be under here. And we're going to call this one Lab 2. Okay. And what I'm going to do, let's get some, before I do that, let me just pick a transistor. NPN. Right there. You just make it smaller a little bit. Okay. That looks good. And then get my wires. Get my resistors. Get my source voltages. Now set some values. Again, the reason I picked 15 volt is why? Because that's what you have in your trainer, if you're going to be using the trainer. Part 3, I had you use the 30 volt, which means go use the DC power supply at least. So this here is just an assumption that that's what you're using, 15 volts, DC. We're going to call this one VCC.
So the inverter production on the
Oh, I see. And we're going to do 15. Okay. This one here will be VBB. And right now, I'm just going to put 0 here because I'm going to show you what I'm going to be doing. Let's read again. What is it we're trying to do with what? Part 1. I am trying to measure VBE versus IB. You with me so far? If I keep this circuit the same here, right? But I can modify this, keeping this resistor here. I can play with IB. Do you agree? And I can measure VBE to see what it does. Do you agree? Right? So I could do it one at a time, or I could do it. So here I decided that with 15 volt, if I put a 1K here, what happens? The max current saturation will be 15 milliamp. It's by design. Could I have picked a lower resistance? Absolutely. Could I have picked a higher resistance? Absolutely. What if I wanted to be at 5 milliamp? I can. If I want a saturation at 5 milliamp. It's just a different operation, right? So I need to divide 15 by something to get 5. Do you agree? And that would be 3K. The higher this resistance, the lower the current in this branch is going to be. The lower this resistance, the higher this current in this branch can be. You're just allocating or allowing for that to happen. You're setting the range. Does that make sense? Now, but that range is going to be dictated how this transistor behaves. Because what is this transistor doing to this Kirchhoff node? It's increasing VCE or decreasing it. You with me so far? By doing that, then the difference of voltages between these two is what IC is, divided by this. The extreme situation where the transistor is saturated, which means VCE is 0, then if you do Kirchhoff, it's only 15 over 1K. That's the max current you'll ever get. The moment this transistor stops opening up, which means that now I have voltages on VCE, then IB decreases because it's the difference in the two voltages here divided by 1K. The numerator will always be lower than what you started with. So far, so good? Okay, good. Now, I picked 100K. We'll explain that. And let's see what happens when we try to run this. Now, before I do anything, I need a reference. And let's go from here to here. Now, I do this on the Mac, so it's slightly different. So bear with me if I'm a little slow here. On my Mac, it's just right mouse click, boom, boom, boom. I can do the whole thing. Here, I have to go back and forth. All right, so let's go to the lab. And it says, sweep VBB at a rate of 0.5 volt per measurement, starting from 0 and ending at 15. So yeah, I could use a secondary power supply and do what? 0, 0.5, have a voltmeter against it. You with me so far? And then while I'm doing that, measure VBE. And how do I know what IB is? VBB minus VBE divided by RB. Can I measure IC at the same time? Sure. Measure VCE and, or just basically VRC and divided by RC. Do you agree? And that's how you're going to collect. So the point out of this is you want to collect. So for various scenarios, VBB, 0.5, 1, 1.5, etc., what would be IB? What would be IC? And what would be VC? This is a good way to put it all together. You with me so far? But you only need to extract later on to graph this is just these two columns.
What two columns?
Yeah. I want IC versus what? Versus IB. You with me so far? But we know everything is related. Do you agree? I just want to see for each scenario what goes on. So I'm going to have to set up my simulator to do a sweep automatically, and then see what it will graph for me. You with me so far?
Yes.
Especially if I'm comparing VBE to IB. You with me so far? Well, let's see it. In my case, I know every time I increase VBB, what happens to IB?
Decreases.
It increases.
It increases.
Yeah. Yeah, I mean, how would I generate an IB here? I need more voltage. Do you agree?
Oh, IB.
Right. Do you agree?
Yeah.
If I'm at 0, IB is 0. So what's the transistor doing now? If I do an up at 0 volt, watch this. Let's go back to here. Let's just do DC operating point, .op. Real simple. This is what you, notice what it says. At 0, IC is 1.5 10 to the minus 11. You can't even measure this. You with me so far? These are 0 current. 10 to the minus 16 for IE, 10 to the minus, I don't know, for 11. Impossible. Does that make sense? It means the transistor isn't even operating at this stage. Why? Because I'm not driving it. I'm not injecting an IB in there. Does that make sense? I'm starting at 0. I did that on purpose. I have a starting point. So the transistor is off. In other words, if it's off, can I figure out, okay, what's VC? Yeah, let's get a point here, and let's call it C. And I'm going to stick it right here. Right? So I want to know what is C to ground, and what is B to ground. So I'm going to call this one B. Right? And run it again.
No E?
You can put E, it's to ground for now. E becomes more important when I put a resistor down there. We haven't done feedback yet. That's coming. So we get to see later on, because that's a good question. Why would we want a resistor at the emitter? What if I didn't want to depend on beta? What if I needed more control? I need feedback, just like any other circuit. Your ear, when you're listening to the radio and you want control, what do? You adjust based on where you want to be. Do you agree? It's too loud. It's too low. So you can gauge it with an RE later on to figure out what your amplification factor should be. So right now, it's basically raw beta that's the transistor is offering for that scenario. You with me so far? There is a certain level of unpredictability and instability. If you want beta to be stable, then we will put a resistor in RE on top of that. But we'll get to see that. That's next week coming up for this, or maybe at the end of this week. So right now you can see here that VC is 15 volt, which, what does that mean? VCE is 15 volt. The transistor is off. It's open circuit. There is no IC. So right there and then, that tells you what goes on. So I don't want to do OP. Let me just go back here. I want to do a DC sweep. On VBB. So name the source, VBB. That's how you do a DC sweep. You're going to tell it how you want to increment VB, from what point to what point, and how you want to increment it. I want to increment start value. So DC sweep, I want it to be linear. Start value at 0, where we are, and stop at 15. That's what you would do in the lab, in increments of 0.5. Is everybody watching what I'm doing here? So instead of .op, I'm using what we call a DC sweep. This is going to simulate what you're going to be doing in the lab in split second. In the lab, this is going to take you probably an hour. Does that make sense? Then I'm going to say, okay. All right, now I'm ready to run it. Now watch this. It's waiting for me to look at, for the different scenarios of, notice here at the bottom, what is it based on? On the voltage of the VB. Does that make sense? So I can lay that against IB. IB is going to increment proportionally. Do you agree? So in other words, if I want to measure VBE versus IB, all I have to do is probe B to ground. Let me do it. And let's see what happens here. Aha! What happened? Anybody can interpret this? Can you see the green? Right. No, that's not it. No, not yet. I told you that VBB is similar to IB. Do you agree? Because it's going to increment the same way. These are not the values for what? IB. Can I get them? Yeah, you're going to have to subtract what? VB minus whatever these values are divided by RB. Does that make sense?
You take all the values divided by RB?
Yeah. So let's say I want to know here at 2 volts, what do I have for VBE? VBE is about almost 0.75. 2 minus 0.75 divided by 100K gives me IB. I'm done. Does that make sense? But notice what's going on with IB. Staying there? Same. Wait a minute. And it had an elbow. If you inverted this, it would look like this. This is VBE, and this is IB. What the heck is this? It's a diode. That's the behavior that I'm looking for. It's part of the characteristic. Does that make sense?
So the top one is the VC.
So what is this telling me? That this is here, VBE. Do you agree? And this here, obviously it's VBB in this graph, but I can find the equivalent, what? IB for that particular point, or any point of VBB. You agree? I just pick a point, right? 6 volt. All right, well, 6 volt, what do I have? I have 0.8. So 6 minus 0.8, that's 5.2, divided by 100K, that's your IB. It's Kirchhoff. And you're going to find that every time you subtract this from this, divided by that, it's always what? Yeah, it's going to be pretty much the same. Does that make sense?
So it was like the 6 volts minus the.
So,
0.8 volts.
so what's happening with IB? IB will increase once it passes the 0.7 volt, do you agree? Right? So, how am I increasing it? By increasing VBB. I have one scenario here at, let's say, 0.5 volts of VBB. What happens? At 2 volts of VBB, it's giving me this scenario, let's say 10 microamp, whatever that is, that's going to be around 0.7. So VBE will remain at what? Almost 0.7 throughout. That's the whole point. Before that, if the voltage is below 0.7 volt at VBB, just like we did with diodes, it's an open. You with me so far? VBE will follow what you're doing. Kind of. Because you need an avalanche. Does that make sense? That's why it is curved instead of being a straight line like this. Otherwise, it will be a linear, boom, and then it will do that. Does that make sense? So, again, so now I just need you to pay attention what value that is, right? Can I rerun the same scenario again? Let me just reduce this one. Just once. Just to see if this shifts at all. You with me so far? Right? So, okay. Let me go back here. Let me close this. I'm going to go over here. By the way, before I do anything, let me run it again. Need you to pay attention to what is it averaging about, a little less than. So if I do this, it's about 0.72 or 0.73. Can we take that?
Yeah.
All right, 0.73.
What would that be for?
0.73 or 730 millivolt. Do you agree? 0.73 volts. Now, what I'm going to do is go back here and decrease this to 5. That means I can't drive enough current anyway. Do you agree? So I'm going to be really a low threshold here, which means the transistor is not going to be as heated. What happened to the diode as the diode got heated? Started drifting. You with me so far? Let's see if we see the same effect. That's what experiments are about. Don't be shy. Explain why you're doing that. Does that make sense? So you're lowering the total power to this one and run the same scenario. All right. Well, let's run it. And I'm just going to measure here. It wasn't enough, but it was still the same. Does that make sense? Yep.
So what's the Y column and what's the X column?
Okay, so what's in here? This is VBE, and that's what I'm measuring with my probe. Does that make sense?
Wait, that's VBE or
VBE.
Okay.
VBE, or is basically VB, to ground. This here is VBB since my sweep is based on it. But, in your case, you're going to be doing what? IB versus what? This one is different. This is part 2. IB versus what? VBE. This is part 1. Does that make sense? That's all you're doing. For the different VBBs, you're looking at IB versus. Can I look at what IC is also? Right? So I can click here. And what is IC doing? Wow, this is interesting. It started out so I'm getting 5 volts from here to here because the transistor was open. Do you agree? I'm measuring. This is VC. This is VC. What's happening? It decreases. Why? Because IC increases. And so saturation down here, I'm at IC max. Does that make sense? So if I were to use this transistor at all in this scenario, then I want to be in this region. Otherwise, you're at cutoff or saturation over here. Think about it. You need to be able to interpret what you're looking at. Does that make sense? What is it I'm looking at? for various VBBs, remember I'm sweeping for VBB, which means various IBs. What happens? As IB increase, IC does what? Increases as well. Do you agree? Right? But how? Well, I'm seeing it from this point. This is what I'm measuring, which means I'm looking at VCE. If VCE decreases, IC is increasing. And then I can subtract VCE from VCC to figure out, okay, what is my IC? And then I can do the calculation from there. But I spared you that, and I did it in a separate one. You could do it right here. Does that make sense? All in the same circuit. Let's go to 50 volts. So now I got 50 volt. Let me run this. And let's measure VB. And notice there's a slight shift up, actually. You may not see it, but I see it here, than what it was. It was still at 0.8 almost. Does that make sense? It's just a small drift, which is nice, because at these levels, you're doing okay. You with me so far? So you could see here, this is VB is basically, or the junction between the base and the emitter is basically a diode. You've proven it with the measurements. Is everybody clear how I got this? Okay, good. All right, so now I'm going to modify this to, let's see here, part 2, where I am going to collect from the same voltage source, but this time I'm going to do a sweep, or go and collect values by changing what? RB. And then measure IC versus what? So part 2, I'm going to measure IB and IC. So VBB will remain 15. I want to measure what IB and VBE for various RB. Right? Starting at 100K. What is the next value? 200K, etc. Then I want to collect IB and IC. That's why I'm looking at part 2 now. You with me so far? Part 2 is IC versus IB. Could I have done it with the same circuit in part 1? Not a big deal. But now, I'm going to build this one here to make it easy for me to do this. So, go back to 15 here.
So in part 2, are we also checking for VCE?
Yeah, so for, let's see here if I can get the delete. Where's the scissor here? There it is. So I'm going to take this, right here, and then get a wire. And that's it. So this is part 2. What did I just do? I just tapped into VCC directly as my VBB. You with me so far? So they're both 15 volts. The only difference is I'm going to be changing the RB here. So let me just name this one as RB. And this here is what? RC. Just so the labels match. And I'm going to go back to the simulation. And do you see here it says DC VBB not found, which is great. So that means this simulation here is no longer valid. You with me so far? We're going to go to DC op and actually delete all of this stuff here. Give me the scissor. Here.
So what do you change? Is it still a sweep?
Yeah, I'm taking it out. So now I'm just simply going to do a DC op. So, DC op, running. This is telling me at 100K, my transistor should be saturated. Is it? Yeah. Almost 0.8. Does that make sense? Okay, great. What is VB? 0.8. VB, isn't it? So what is my IC? Well, it's 14 milliamp. It's pretty up there. Does that make sense? So I'm saturated. That means my IB Notice the ratio between them. So I have a 14 versus 0.14. 14 versus 0.14. Can you tell me what is beta based on this? What is IC over IB?
How's IB 14?
14.
14, and I'm at 0.14. Notice, here, you can see it right here. Do you agree? I'm just interested in the ratio. I don't even need to figure out if it's milliamp, microamp, well, I don't care. It's the same, they're the same scale. Do you agree? So what's the division of 14 divided by 0.14? 100. So we assume for this case, beta is what? 100. Great. Go back. Guess what I'm going to do? I'm going to go to 200K and run it again. And see if we get the same beta. So, notice now VC is what? 7, it's half of VC. We're right in the middle of the load line. And so that's great, but I'm only interested in what? And so remember, as I increase this, what happens to IB? Decreases. So what happens to IC? Decreases. Did it? Yes. It's 7 milliamp for IC. Oops, I got this backwards. 0.14 here and 14. So I've got IC is what? 7 milliamp. So this is in milliamp. And this is, you could do this in milliamp or you could do it in microamp. Right? So if you did it in microamp, then this is 140. Do you agree?
So wouldn't beta be different now?
What would it be different?
Beta.
Beta still is 14 milliamp divided by 140. I just changed the unit. Does that make sense? The multiplier.
Okay.
And the reason I did that is because as I go down here, my IC and IB are going to be smaller. I need to be within those values. Does that make sense? So what happens? 7 milliamp. What do I end up with? What does it say? At 7 milliamp, I'm getting 7 10 to the minus 5. So that's 0.7 microamp. Do you agree? What's 7 divided by 0.7?
100.
You with me so far?
Yeah.
0.07.
Is it? I have 7, but I want it to be 10 to the minus 6. Move the 0 here. Do you agree?
0.7.
Right. Yeah, I want micro, not minus 5. You with me so far? Minus 6. All right, so move on next value. So I'm just going to cut to I'm going to put 1 meg here. Yeah. Well, let's put 500K. All right, run it. At 500K, somewhere around here, I'm going to get way smaller. So I have a 2.8 milliamp. And guess what do I have here? 0.028 microamp. Again. So what is it telling me? For all that range, beta cannot remain the same. And what is beta for this transistor based on these scenarios? 100. And that's the relationship of IC equals beta IB. Explain again where it came from. That's how they're related. The beta keeps it all together. You with me so far? That's the glue between the input and the output. It's the mechanism that keeps or throttles the current for the output based on what you're doing at the input. Do you agree? As I'm changing RB, I am lowering. As I'm increasing RB, I'm lowering. So the more you increase this impedance here, or resistance, I am lowering the amount of current that goes through here. Do you agree? It's a current limiter. As I lower the current that's in here, and we had to prove there is a relationship between IB and IC. If this gets lower, then this gets lower too. And if it doesn't proportionally, well, then I need to know what that proportion is. That's beta. So far, so good?
Yeah.
All right, that's part 2. You can do this in the lab. All right, so now we're going to do what? Part 3, which is a little trickier. And then for part 3, we get to see that I'm going to need to stabilize IB and give it a sweep. You with me so far? For different IBs, what would be the sweep? And notice here, so I'm just going to go back to the lab. You can see here that I am sweeping VCC as my primary and IB as my secondary. You with me so far? So I have 2 sweeps going on at the same time to get something like that. Prior to that, the first example we did with the sweep right here, there was only one sweep, which was VBB. Does that make sense?
So the BBB was changed to that.
Right, so part 1, only VBB was changing to collect the data. Now I need 2 scenarios. The same scenario, but one, it's like a loop within a loop. You with me so far? I want the outer loop to iterate and then the inner loop to iterate several times. When it's done, then iterate the outer loop and then do the inner loop. It's a for loop within a for loop. You with me so far? That's all it is. You decide the order of the sweep. Well, the outer is the front. Does that make sense? And the inner, or vice versa. We'll see. So, let's see what happens. True. So we want to do this. And notice here I changed it on purpose because if you measure the current here, it's going to be the same here. We could do that with a .op and see what happens. Now, notice here I've increased this one to 30 and this one to 150. Same transistor. What's my aim here? It's to really look at a bigger quadrant with much higher currents. You with me so far? So I can actually see, could I have done it with the 15 volt and 1K? Yeah. Yep.
In the diagram, it has VCC at 30, but in the description below it says to go VCC 0 to 15.
Where?
Step 1, maintain IB.
Oh, maintain IB constant.
From 0 to 15.
Yeah. It's just so 30, but up to 30. Does that make sense?
Up to 30.
Up to 30.
Okay.
Yep, that's all. So we start from 0 up to 30. I should have written 0 here. I'll write it up as 0 when I do my simulation. But notice VCC is from 0 to 30 and I'm moving by 5 volts. And then my current generator is starting from 0 amp or 0 microamp to a max of 0.5, which is 500 microamp, or 500 microamp in increments of 50 microamps. Does that make sense? These are my steps. So that means your first 50 microamp from 0 will be here. You with me so far? This would be for 100 microamp. This would be for 150 microamp for IB. You with me so far?
So we're changing RC and
So for this, I need to change my current. You with me so far? To get these currents, that's why I use a generator. In your case, in the lab, what are you going to do? You're going to change VBB and RB. You with me so far? To get to remain within that current range until you're done with all your VCCs. Then come back, start VCC at 0, give it another current. Does that make sense? And then go from there. So, this is going to require that you sit in the lab and do this a lot. Does that make sense? All right? I will swing by the lab to see what you're doing. And you should be really, really busy doing this. So let's go ahead and fix this circuit. So let me get the scissor again. Where's my scissor? Get this. Let's draw. Scissor. Let's do it differently. Okay, so what I'm going to do is put a resistor right here, and then put a resistor this way. Draw. Oops. Go. Then go to my components, current, this one, and we say okay, but flip it around, otherwise it's a negative current going this way. So Control R, Control R. I can call this one IB if you want to call it, just left it this way. So now I got to put some values here. What values did I have? 200K and 100K. And we get to measure quickly. So I have 200K for this one. And this one is 100K. For now, I'm just going to set this up straight up to 30 for now. And this one to 150 ohm. Let's just run it the way it is. Yeah? So I'm just going to run it the way it is and see what is my system doing. Does that make sense? So right here, I didn't set any current. Well, let me, just for the giggles, set it to 0. That means there's no current going to IB. If there is no current going to IB, you're not driving the transistor should be cut off. Does that make sense? If that's the case, then VC should be VCC, 30 volts, and IC should be 0. If you understand, that's the first assignment I gave you to go home and go to the corner and work on. You should be able to converse, at least figure out, okay, what's going to happen if I did this in there? Predict it. Does that make sense? Because you understand how the transistor behaves. It has no IB current. You're not driving the transistor, then it's off. If it's off, then VCE will be equal to VCC. In other words, IC is 0 amp. Well, sure. IB is also 0 amp. Does that make sense? So go ahead and run this. Let's go ahead and run it, and I can measure. I'm going to measure IB. Look at that. Obviously, you're not going to get this in the lab. It's 0 amp. Does that make sense? And what is IC going to be doing? 0 amp too. And what is VC going to do? VC is VCE for this case, right? 30 volt. Transistor is off. Or what we call cutoff. Does that make sense? So we're in a cutoff. Okay. All right, so what would happen if I change this to 10 microamp? Now, you could sit here and do all this all day. You with me so far? Right? So this NPN transistor here was, oh, I didn't change it to 3904, did I? That's why it was giving me 100. That was a default beta for that transistor. I'll leave it. Doesn't matter. This experiment should work with all transistors. You with me so far? I'll leave it at 100. You do it for the 3904. So, let's see what happens. I'm going to run it. Notice now VC went down a little bit. That means I have a little bit of current in IC. You with me so far? And where does IB? Well, IB is 2.6 microamp. IB going to the base, so that means it's a portion of this 10 microamp. You with me so far? Great. So I've got this current here is 10 micro, which means I have 2.6 microamp going to the transistor. Do you agree? Mm-hmm. In other words, what am I getting at IC? Well, looky here. I'm getting what? 260 microamp. What's my ratio? 100. Does that make sense? Good. Let's do it again. More. Let's go to 50 microamp. That would be the increments that I want you to do.
And
So-
how do we get those increments? Where you just
I haven't done the sweep yet. I'm just doing it manually. Does that make sense?
Yeah, but in the lab, where we just have like.
In the
two
lab,
resistors,
in the lab, you're going to increase VBB.
VBB, or.
Yeah, you're going to increase VBB. Sometimes you're going to have to adjust RB to always get the same current. You with me so far? So, what's going to happen here if I run this? Well, lo and behold, notice this is going to reduce VC. IC is going to go higher a little bit. Do you agree? Now I have 4.1 milliamp versus what? 0.41 microamp. Still a ratio of 100. So the rules of the transistor are still working the same. So as I increase this, let's say now we go to 200 microamp. I'm just cutting to the chase here. Let's see what the transistor is doing. Notice now I'm dropping to 27 volt for VCE. Does that make sense? So I don't have enough. I am still in the kind of close to the cutoff region. Currents are very small. Why? Because look at IC. It's only 19 milliamp. Does that make sense? Right? Considering I have, what, 30 volt over, if I were to go to saturation over the 150 ohm, that should be a huge current. So let's go to 1 milli. That's a lot of current for the base. Let's run it. Okay, dropped it by half. VCE now is half of the source. What happened to IC? Obviously, it's got to have to go up, which is 99 milliamp. And notice your IB increased to 991 microamp. And the ratio is still 100. That's what the simulator is modeling. It's modeling a transistor that has a beta of what? 100. In the lab, you could be using a 2222 or 3904 or whatever it is. You're going to have to figure out what is beta initially. Does that make sense? By looking at the relationship between